Okay, now I'm going to talk about Fischer projections. Fischer projections are a nice, easy way to draw 3D chiral molecules, or actually not 3D, but represent three-dimensional molecules that are chiral in an easy to understand two-dimensional way. Now we're building up to talk specifically about drawing carbohydrates. So we're going to have hydroxides involved, but a Fischer projection is basically this. The chiral center is shown as the intersection of a vertical and a horizontal line. So here is a Fischer projection, where the carbon is considered to be in the middle, and what we have is we have four different things on the outside. Now, to give you a better picture, here's what's really being shown. Remember, these two things on the sides are coming out of, are being projected out at you. So the two things on the left and right are being projected out at you, and the two things up and down, the dotted line, the dashed line, are going away from you. So if you consider this, I'm going to do A, B, C, and D again. And if I were to actually tilt it down and turn it, so I'm going to bring it down at you towards you, it'll end up looking like this. Right? I've tilted it forward on its side. So A is now leaning forward, C is actually sticking back, and D is on the left leg, and B is here. So B came down, D came down, A came forward, and C swung around to the back. And now I'm going to tilt it down and sort of twist it. So I'm going to tilt it straight down so it'll look like carbon here, D is going to be going back, B is going to be going back, back. D is going to be going back, B will be going back, A is coming forward, and C is straight up. And now I can twist it to the right a little bit, and I'm going to get D straight out here, A, B, C. This can get really, really nasty to try to follow and go in and out. But I may ask you to convert between a Fischer projection and a projection like this. So you'll want to practice that a little bit. So here are left and right glyceraldehyde. So here are two different glyceraldehydes. These are enantiomers of each other because here's a mirror. These are mirror images, right? So if we swap the left and right arms, we have the enantiomers, right? So it's changing about a chiral center. Handedness, we specify which one we're talking about. See the L, and the D by looking at the hydroxyl group. Now this doesn't work for everything because not every compound ever is going to have a hydroxyl group. This is very specific to carbohydrates, which is all we're really going to deal with in Fischer projections. So the left one, L, is where the Fischer projection, the hydroxyl is to the left. Now, the other thing I should say is the double bond, the carbonyl, is farthest to the top as we can possibly make it. We always put the carbonyl at the top. So the aldehyde group is at the top. And if it was a ketone, if we had something like this, if we had CH2OH and we had a ketone, we put the ketone at the top. And this, and then what we look is we see that this is going to the left over here, right? So that's the L. If it's going to the right, it's D. D is Greek for dextra, meaning right, right-handed, dexterous. This one I've drawn over here, this would be a D enantiomer, right? Because here's the chiral center. The hydroxyl group is going to the right. So that is a D designation. However, we can sometimes have two chiral centers. So now I've got four possibilities here. I have four different possibilities for chiral centers. We identify them as D and L by looking at the highest numbered chiral center, or another way to think about it is if the aldehyde or the carbonyl is at the top, then the one at the bottom, the lowest chiral center is what designates D and L. So since this hydroxyl group is going to the right, that's a D. Since this hydroxyl group is going to the left, that's an L. Here it's a D, L. We always look at the last one to call it D and L. That's how we designate them. Then you might ask, how do I differentiate between them? I've got 2 L's and 2 D's now, Steve. What do I do? Well, we have common names for them. We just give them different common names. This is called D-erythrose. This is called L-erythrose. This is important to realize. These are enantiomers. In order to be enantiomers, every chiral center has to be flipped. You see how they're mirror images, right? The hydroxyl group on the left, left, right, right. They have to have every chiral center flipped. These are not enantiomers. These are, in fact, diastereomers, right? They have different chiralities, they have different arrangement, they are stereoisomers, right? But they're not enantiomers because they're not mirror images. But they are diastereomers. More specifically, they are epimers. Epimers are molecules whose molecules differ only in the configuration of one chiral center. So these are epimers because they differ in one chiral center. These are also epimers, right? But so since this one over here is D-erythrose, that makes this L-erythrose, right? D-L. This is D-threose. This is L-threose because they're total mirror images of each other. And that is really what you need to know about Fischer projections for carbohydrates. You need to know how they're always arranged. We've always got the aldehyde or the ketone at the top. You need to know how to identify D and L. And you need to know that in order to be enantiomers, every chiral center has to flip.